Hey everybody, Dr. Retzig here. This is our third video in section 7c. So far in 7c, we've considered the so-called positive operators, and now we want to turn our attention to another kind of operator, the isometries. Let's get started. Okay, so here's the setup. As usual, get a finite dimensional inner product space V. You got a map S. Inputs from V, outputs from V. So S is an operator on V. So it takes inputs little v and then spits out outputs S acting on little v. To be an isometry is to have the property that the norm of the output is the same as the norm of the input. Definition. S, a linear operator on V, is an isometry. That's the term we're defining. If the norm of SV is the same as the norm of V for all V in our space. So an isometry is an operator that preserves norm. Okay, let's look at a couple of concrete examples. Example. What if we had R2 as our inner product space and T mapping R2 to R2 according to if you feed T that vector in R2, call it V, then T simply rotates the input vector by 90 degrees counterclockwise. So that's TV there. Now you can see V and TV are definitely not the same vector, but they definitely have the same length. After all, we only rotated the green vector. We didn't change its length. And so this example, rotation, is an isometry. This T is an isometry. Example. Not everything's an isometry. That would be nice, but that's just not the case. I mean, just imagine any mapping at all that has 3 as an eigenvalue. That means some vector goes to 3 times itself. So the input and output are definitely not the same norm. Even more simply, how about T, an operator on V, given by T equals 5i, so 5 times the identity, is not an isometry. On this one, outputs are 5 times the size of inputs, norm-wise. Okay, so some operators are isometries and other operators are not isometries. And we'll be interested in some sort of characterization here in 7c. Exactly what are the operators that turn out to be isometries? We have a characterization like that for the positive operators. We want something similar for the isometries. Now, if you're looking to build an isometry, then there's one clear-cut way to do that for sure. All right, let's say you got an inner product space V. Nothing specific really in mind here. We're going to define S in a really concrete way so as to force it to be an isometry. So if you're ever trying to cook up an isometry, you can always cook one up according to this example. Okay, so you got your finite dimensional inner product space V. Let's just grab a orthonormal basis in V, and let's define S from V to V by, okay, here's how it's going to work. If we tell the reader where each basis vector is sent, then we have told the reader where any vector is sent, because any arbitrary V in that box can be written as a linear combination of the E's. Here's what S is going to do to the E's. S acting on a typical EJ, we're going to make those into genuine eigenvectors for S by declaring S acting on EJ to be some scalar lambda j times EJ. And our only insistence is that the absolute value of the scalar is 1. Okay, if we build ourselves a map in that way, send each of an orthonormal basis to a scalar multiple of itself, where the absolute value of that scalar is 1, then we will have built an isometry. So let's justify that claim. Claim S is an isometry. Proof. Okay, well, we know the definition. To show that S is an isometry, we have to show that an arbitrary vector V gets mapped to an output SV of the exact same norm as V was originally. Okay, so let little v be an arbitrary vector in big V. So little v is maybe here. Okay. Well, E1 through En are an orthonormal basis. So in particular, you can write V as a linear combination of them. So let's say V is, I don't know, A1 E1 plus dot 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 AN En. Okay, so just grab a little vector V and express it in terms of the E's. Okay, well, S is a linear map, so S acting on V is S acting on A1 E1 plus AN En, which is A1 S acting on E1 plus dot 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 AN S acting on En. But we know how S acts on the E's, so that's A1 lambda 1 E1 plus dot 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 AN lambda N En. This is by design. We created this mapping S in this way. Okay, so now check this out. SV is a linear combination with the coefficients underlined in purple of an orthonormal basis, E1 through En. Well, you guys are really good at this in a chapter 6 sense. So the square of the norm of SV, remember, E1 through En are orthonormal, so it's easy to read off. It's A1 lambda 1 absolute value squared plus ... An lambda n absolute value squared. That's how you find the norm of a linear combination of orthonormal vectors. But by choice, the lambda 1s, lambda 2s through lambda n's, those are all absolute value 1. So in fact, this is absolute A1 squared plus ... absolute An squared. But that's just the sum of the squares of the absolute values of the coefficients for V. So that's nothing other than norm V squared. And that's it. So the norm of SV is the same as the norm of V. So anytime you're in the market for an isometry, you can definitely create one. If you have access to an orthonormal basis, it's easy to build isometries. Just make sure you send each orthonormal basis vector to some scalar multiple of itself, where the scalar multiple is of absolute value 1, and you will have built an isometry. Now, let's not overreach here. There are isometries that are not built in this way. See example 1. There aren't even any eigenvectors for that, right? You agree that no green vector gets sent to itself besides the 0 vector. There aren't even any eigenvectors to be had, so there's certainly not an orthonormal basis of eigenvectors. And yet, example 1 was an isometry. So nobody is saying that every isometry arises in this way. We are only saying at this moment that mappings that arise in this way are isometries. Now, you may be not so surprised to find out that if your inner product space is over the complex field, this is in fact the only way that an isometry arises. But example 1 shows over the reals, there are isometries that don't arise in that way. Okay, so zooming out, an isometry is just a linear operator that preserves norm. And we've seen a few concrete examples, and now we want to characterize them. We want to say T is an isometry if and only if blah. What is that? And that's the topic of the next video. All right, I'll see you next time. Bye.